Okay, let's talk about projectile motion and the angle for maximum range. And I've been doing this, right? I've been doing some numerical calculations for projectile motion, and I did it. And I showed that if you shoot a ball with air drag, 45-degree angle on flat ground is not the maximum range, and for the most part. And then someone said, but wait, whoa, what about that super crazy cannon from World War II? I heard that it had like a launch maximum angle at 52 degrees, not 45, not lower than 45. And I said, oh, really? So let's find out. So I don't know the answer right now. I'm starting this. I don't even know the answer. I have not done the calculation. So you're going to be just as surprised as I am, but let's get started. So this is the Schwerer Gustav. I don't know anything about the history of this stuff, okay? It's a huge cannon, and it exists. It's so big, they put it on this railroad track and stuff like that. Has a barrel length, 32 meters, 80 centimeter caliber. We'll need that. Launch velocity of 820 meters per second, 47 kilometer range. And then apparently there's two different ways. You could have a 7,000 kilogram thing. Is it a shell? It's not a bullet. At 720 meters per second with a range of 38 kilometers, or the 47 kilometers, 48. Now, I got that wrong. Okay, is 4,800 kilograms. So, whatever. I'll just go with the 4,800 kilogram mass. We can change it later. So, let's review no air drag. So, if I have projectile motion without air drag and I shoot it at different angles, so here's 3 different runs, and if you want to go, I'll link it down below. I've already done this. So the blue arrow, the blue line, is a trajectory plot for 35 degrees. The green is 45, and then the red is 55. And you see that the 45 and the 55 and 35 are the same range, but the max range is 45. I don't think there's any mystery there. I just want to show you that. What if I add in air resistance? And I've already done this. Okay, so this is a review. It depends on the velocity of the object. I'm going fast. The cross-sectional area of the object, the density of air, the shape. And so here's a ball moving through the air, has some velocity v, air drag's pushing it in the opposite direction of v, so I need that unit vector v hat, and I can use this model. Negative 1/2 rho, that's the density of air, a, the cross-sectional area, c is the shape. I have to find the magnitude of the velocity squared, and then multiply by the unit vector to get a vector force. And then so the problem here is you can't do that in closed form, because the squared velocity depends on both x and y direction. If it's in 2 dimensions, you can't do this. But you can do it numerically, so that's what we're going to do. So the idea is to break the problem into small time steps and do the following during each time step. Calculate the force. So that's just the gravitational force plus the air resistance force. And I'm going to assume during this short time step that force is constant, and that's the key. If my time step is small enough, then that force is fairly constant. I can use that force to update the momentum. And again, I'm skipping over this because we've done it. I can use that momentum to update the position, and then I can update time, and then repeat the whole thing until you get blue in the face or bored, or the ball gets back to the ground, or you have to stop and go take out the trash, or whatever you want. So that's the idea of a numerical calculation. If you do the same 3 launch angles with air resistance, it might look something like this. It depends, though. It depends on the velocity and the mass of the ball and all this stuff. But here you'll see that the 35-degree ball actually goes farther than the 45-degree ball. And probably the maximum range would be 41 or 42. It just depends. And why is that? Why does it go farther at a lower angle? It's because of time. Think about it in terms of time. If I have this air drag force that constantly slows it down, and I shoot the ball too high, then it's going to spend a longer time in the air, and that's going to have a longer time for the velocity to slow down. If I shoot it at 45, that would normally be the maximum range, but now air drag slows it down. I want to actually shoot it lower so that it doesn't have as much time to slow down, and in fact, I get a longer range, and that's for normal cases. So that's where we've already done that. Okay, now we're at a new part. So what about the Schwerer Gustav? This is another picture I found of it. I think this is after the Allies captured it, they're like, hey, let's stand on it and take a picture. I think that's the same cannon, isn't it? It looks like the same one. Okay. So if I shoot this ginormously large projectile and it goes super high, is the gravitational, do I have to take into account the curvature of the Earth and the change in the gravitational field because it goes further away from the Earth? I don't know. Let's find out. And do I have to take into account the change in the air density? I assume at least I have to take into account the change in air density. So let's think about gravity first. So here's my normal gravitational force. If I'm on the surface of the Earth and I don't go too high, I can say the gravitational force is m, the mass of the object, times g, where g is the gravitational field, has a negative 9.8 y component newtons per kilogram. Of course, that's just an approximation. A better model for gravity is this. It depends on the universal gravitational constant g, the mass of the Earth, the mass of the object, divided by the distance between their centers squared. So that'd be the radius of the Earth plus the altitude, I'm calling it y, and then squared. Okay. And then I put a y hat there just because I was assuming it's still in the y direction, which I think that's okay. So how different are these values going to be? So let's look at a situation. Suppose I take the cannon and I shoot it straight up and there's no air resistance. So it has a 820 meter per second velocity. There's no air resistance. So I know it's not going to go as high as this calculation is. Okay. I can use the work energy idea to find out how high it goes, and then I can say that's my maximum height. It's definitely not going to go that high. So let's shoot this straight up. It has initial velocity v0. It goes a height h. I use the work energy system. As the system, I pick the ball plus the Earth, and so there's no work done, but I do have a change in kinetic energy and a change in gravitational potential energy. And I'm using the real, not the real gravity, the fake gravity. So that's going to be zero work. The final kinetic energy is 0. The initial is negative, 1/2 mv squared. The final potential is mgh, and the initial would be 0 if I set the potential of 0 at the ground. And if I solve for h, I get v0 squared over 2g. I plug in my initial velocity, I get 34 kilometers altitude. Okay, so that's how high it's going to go if there's no air drag and the gravitational force is constant, both of which are not true, but it's a good approximation. So now I can put in it actually go higher, okay, because the gravitational force would decrease, but I think that's a good approximation. So if I take a mass of 1 kilogram and I use the Earth-based constant gravity of 9.8 newtons per kilogram, I get a force of 9.8 newtons. Now if I take the radius of the Earth and I add in 34 kilometers, I get this, 6.405 times 10 to the 6th meters, and I put that in and I use this for the mass of the Earth, and I put this in for the gravitational force, I get 9.71. So here I have 9.8 versus 9.71. I don't think it's really a big difference because I don't think it's even going to go that high. That's shooting it straight up with no air drag. So I'm just going to not include air resistance. I'm not going to include a changing gravitational field. Is that okay? If it's wrong, it's wrong. We can redo it later. It's not a big deal. Okay. So now we're back to this. What are we going to do? Again, I have calculate the net force, update the momentum, update the position, update time, repeat. But I'm going to need to add an extra step. And I'm going to call that step 0 because I didn't want to renumber. And it would be this. Calculate the density. So before I calculate the net force, I need to calculate the density as a function of altitude. Because as I get higher, that's going to change. So that's really the only thing I need to add in my model here. Well, how do you find the density at altitude? Okay, so you use Wikipedia, which has this very nice explanation about how to calculate the density at different altitudes, and it's a little weird, okay, but it's pretty much legit. So here's, as you move higher, the temperature decreases. L is this parameter, this, what do they call it? A temperature lapse rate. Yeah, I don't know what that means. So what you do is you calculate the pressure as a function of altitude, h in this case, which also depends on the molar mass of dry air and the gas constant, r. So once you find the temperature, you can find the pressure based on the pressure at sea level. And then from that, you can calculate the density. So it's a 3-part process. But that's fine. I have all the numbers. I can do that. And so here's what it looks like. This is, I just made a function in Python, which I'll show you. I've already done this just because I want to make sure it's working. So I can put in my value of h and it returns the density. And then I made a little plot of density as a function of altitude. And this looks pretty good, right? Because over here I have at 0 meters, it's 1.2 kilograms per cubic meter, which I know is the density of air. And then it decreases at some function. And I think there's no reason to think this is not legitimate. And I just plotted up to 10,000 meters, but you know, I think it's going well. So now I can use my density function. I can go back and I can make my numerical model for the Schwerer Gustav, and we're going to do that. So let's jump over to Python, and I'm skipping over there right now. Okay, so welcome back. Surprise, I started without you, couldn't wait. So this is I already told you I entered this function. So here's my density function, and this stuff just makes a graph. But the rest, I'm pretty much starting from scratch because I want to do it with you so that when I make mistakes and things go terribly wrong, you're there to share with me. Okay, so I've already actually entered a couple other things. I have the launch velocity, the mass, the radius of the shell. I assumed it was 80 centimeter diameter, which I think that's what caliber means, and I'm not even sure. And then the area and the drag coefficient, I wasn't really sure. A bullet, I don't know what this shape is. I mean, a sphere is 0.47, and yeah, we're going really, really, really fast, so things don't always work the way you think, but that's fine. We're going to do it anyway. Okay, so now I need to pick, I'm going to do this as a scalar calculation. So let's just say r equals vector 0, 0, 0. I didn't say scalar. I mean, I'm not going to draw it. I'm not going to make a visual. I'm just going to calculate it. I need my initial momentum, so P equals M times V0 times, oh, I need the launch angle. So let's say theta equals, someone said 52, so I'm going to say 52 times pi divided by 180. So it's going to be vector, and I've done this before, so I don't want to spend too much time on it. Cosine theta, sine theta, 0. That's my initial momentum. I think I'm doing well. Okay. So now I want to do t equals 0, dt equals 0.001. And I picked 0. I think this is probably, it's going so fast, that's fine. Let's do while r dot y is greater than or equal to 0. So that's the y component of the position. Okay. So step number 1 is to calculate, actually I'm going to calculate the velocity because I deal with momentum, velocity is in the equation, so I'm going to say v equals p divided by m. And now I'm going to calculate the density. I'm not even going to calculate the density. I'm going to do it all at one step. So I'm going to say F equals, did I put G in there? No. G, I put GG in there. Okay, G equals vector 0, negative 9.80. Okay. M times G minus 0.5 times the density rho of r dot y. You see there? That's what's so nice about making that function, because now I just put in my value of y right in there. I don't even have to have a separate line. Rho times a times c times mag of v, the magnitude. I can't square a vector, and then I have to multiply that by the unit vector norm v. There. Now I need to update the momentum. P equals p plus f times dt. Now I need to update the position. R equals r plus p times dt divided by m. And so I did have someone asked me a question at one point. How come you used momentum here but you solve for the velocity there? And so what I do is I'm using the momentum principle with the forces, and so that's why I have it like this, these two lines. Up here, I have to actually resolve for the velocity because the momentum changes and the velocity changes. But I never updated the velocity, I updated the momentum. So when I get back to the beginning, I need to put in the velocity. Now I could skip all this and just put p over m squared and unit vector p, but I just like putting it this way. It's my program, and so that's just the way I do it. Now I'm going to plot the position. So I can say f1.plot r.x, r.y. I'm plotting the trajectory. Now I'm going to update time, t equals t plus dt. Yeah, let's just see what happens. I'm going to save this. Save it. And yes, I'm going to give you the code. Don't worry about that. And I don't know what's going to happen. Let's run it. Whoa, it worked. Well, it didn't crash. Huh. Okay, so that went, what's that final 41 kilometers? But it looks very parabolic. Okay, let's do this. Let's put AC equals 0. Okay, and actually, before that, let me print this out. Okay, you have to remember, print R. That's the final position. So 41.7 kilometers. Okay, now I'm going to turn off, I'm going to make the drag 0. It went further. Okay, so that's a good sign. Now for the real part. Okay, put this back on. Now down here, let's say rho R equals 1.2. Rho R is the density at sea level. I'm going to put down here rho R. Now, so it went 41.7. Let's see if it goes a different number. Okay, whoa. Whoa, look at that. I think this is working. Okay. So, I'm pretty happy. I didn't get the same value they had. They had 48 kilometers, I think it was. But I'm in the right ballpark, so I'm pretty happy. So actually, let's go back up here and let's try this. Rho as a function of r dot y. And this. I'm going to change this to 0.35. I mean, it's a shell. It's not. It should have a better drag coefficient than a sphere. 44. You see? So I think I'm pretty much on game here. Okay. So now we need one more step. And I'm going to start a new program. I'm going to stop this and start a new program. And that's to make a plot of the range as a function of angle for this particular ball. And if you want to take this code, and I'll save this code for you too, if you want to take this code and then play around with it and do a comparison of no gravity, constant air drag, and so forth, that's fine. But I'm going to stop this and make one more video, one more program, and I'm going to start over. I'm going to put some things in there to start with just to make it a little bit simpler. Okay. Okay, I got a little out of control. I got maybe a little bit ahead of myself, but I didn't really do anything much. I have this part right here. This is the same density function, so no big surprise there. And then everything else, I just made a function called f-range for final range. I don't know what that means, but and it takes the velocity and the angle. I don't know why I put both those in there. And then so everything else is the same, except it's indented in part of that function. And I took out the v0 equals and theta equals, so that's not in there. And then instead of printing the final r, I just return the x position. So you didn't miss anything. So we're cool, right? And then I put the VV as the initial velocity of 820. I didn't want to say it again. I'm starting with an angle of theta. Oh, this is, technically you shouldn't do that. Theta, T theta for temp theta. Okay, I don't want to be inappropriate. So now what I'm going to do is launch. That function returns the range. It does the whole trajectory and returns the range. So I'm going to launch it at 15 degrees and plot a data point for the range versus theta, increase the angle, and do it again and again. So let's say while t theta is less than, let's go up to, I don't know, what do you think, 75 degrees? 75 times pi divided by 180. I need to convert to degrees, I guess, to radians. So what I'm going to do the first thing is to, all I have to do is plot the range, right? So I'm going to say f1.plot the angle t theta times 180 divided by pi. I want to plot it in degrees because I'm a degree-centric kind of guy. And then the range, so it's going to be f range, and then I need to put in the velocity vv and t theta. That's it. See, I don't even need to do anything like that. The only thing I need to do now is to increase the value of t theta. T theta, spell it correctly, equals t theta plus d theta. And I think that should do it. And I feel like there's an error in here, but I'm just going to proceed. I'm just going to save this, and yes, I'll give you the code, and let's run it and see what the heck happens. I'm kind of excited. Oh. Well, that's weird. Oh. Plot. Oh, I know what I did wrong. Ha! Okay, good. Down here. I put the plot in the function. Okay. I was plotting it twice. That's better. Look at that. So now we have the range as a function of the launch angle. And there is the maximum at 48.3. What do you know? Okay, so what is happening here conceptually? So you shoot this ball up, and it's like shooting a ball out of water. You're underwater and shooting the ball. You want to get into lower density stuff so that you have less drag. So when I shoot it up into the air, I get into a region with less drag, so that I can kind of get further without slowing down. If I shoot it lower, I'm in the higher density air, and it's going to slow down more. So that's kind of cool. I think it works. So I think you guys are right. Whoever suggested that, I think it was on Reddit. Good job. Great problem. I had fun. I'll give you all the code down below. I'll link down below the other calculations because I had fun doing them, and I hope you have fun too. Talk to you later.